Good morning, everybody. Welcome to Papa Lim Physics Classroom. Okay, today I'll be going through the MCQ question for Presbyterian High School Prelim paper. Okay, same as before. Okay, if you need the paper, okay, you want to take a look at the paper, okay, you can feel free to download it from my Google Drive. The link is at the bottom below. If you have done it, okay, you might want to check your answer and look at what are the questions that you make mistakes, or what are the interesting questions that you might want to take notes. Okay, same as before. As this video, I will be going through most of the questions. Okay, it will be a long question, long video. So if you need certain explanation or certain answers for certain questions, you can just feel free to skip, scroll to the respective area so that you can get what you need. Okay, now without delaying, okay, let's look at the paper itself. Now, paper 1. Okay. In the paper, I have indicated some of the interesting questions that you might want to take a look. Okay, these are the questions that I find actually quite interesting. Okay, now paper 1. Okay, now the paper is here. Okay, for those who have done the paper, you might want to pause here and take a look at the question, the answers here, just to take a look at how much, what are the mistakes that you might make, or what are the questions that you might want to actually take note of. Okay, if not, okay, let's move on to question 1 here. Now for paper 1, question 1 is straightforward. Okay, which of the pairs of matrices, prefixes have the greatest magnitude? Okay, this one, most students or all students, you should be aware of the prefixes, whether it's giga, mega, kilo, milli, deci, centi, all the 9 prefixes you have to be well versed. So without delaying, the easiest way is to actually work out all the prefixes. Okay, mega is 10 to the power 6, giga is 10 to the power 9, all this, and after that, you use a calculator to work out which of the one have the greatest magnitude. Okay, it's fairly quite straightforward. If you've done it, the option here will be A. Okay, now question 2. Question 2 is vernier caliper. Okay, vernier caliper here is to use to measure the width of the object. Okay, you have a diagram 1 which is closed. Okay, when it's closed, the reading here actually will give you the zero error, okay, of the vernier caliper itself. And with the jaw closed around the object, this particular reading, diagram 2, will actually give you the observed reading. Okay, what you observe from the machine itself. And after that, the final reading, the width of the object here will refer to actually what we know as the actual reading. Okay, the actual reading, okay, to some of you who will remember, okay, there's a formula for it, is what we call the observed reading. Okay, the observed reading, okay, minus away the zero error. Okay, this is one of the formula that we have. Yeah, not just zero error, it's for all vernier caliper. Okay, for vernier scale, the number that you're interested in is the zero marking here. Okay, not the frame here, not the frame. Okay, so look at the zero marking. The zero marking is before 0.1. So this reading here we are looking at will be 0.0 something cm. Okay, 0.0 something cm means the next one we look at would be vernier caliper. The line that the scale, the marking on the vernier scale will coincide with the main scale. So the number that we are looking at will be this particular line. Number 7 line, he will actually coincide with the main scale. So if the line is 7, okay, so this will be mark 7. Okay, and since the zero mark here is on the right of the 0 at the main scale, this will be what we know as your positive zero error. So same thing for vernier caliper. For diagram 2, for observed reading, same as before, you are interested in the zero marking here. This zero marking will tell you the first 2 digits of the reading itself. The zero marking here will actually tell you the reading here is more than 1.5, but less than 1.6. So which means that the first 2 digit for this reading will be 1.5 something cm. So for the last digit, okay, I'll look for the line in the vernier scale that coincide with the main scale, and this line will happen to be the number 5 line. Okay, so number 5 line, you take a look, this line in the vernier scale, okay, will coincide with the main scale, which is this is the line that I want. So this means the second digit here will be 5. Okay, so the observed reading is 1.55. The zero error is 0.07. So if you look at the formula, okay, so the diagram number 1 would mean that the zero error is positive, means is always the measurement taken it will always be larger than the actual one. Okay, so if you look at the formula here, you'll be 1.55 minus 0.07. Okay, so if you work out the math, the final answer here will be 1.48 okay, cm. So this will be the actual reading, which will lead us to answer to be B. Okay, now for those who are like forgot about your vernier caliper, because this is like chapter 1 for like the last year, is a one at least 2 year ago topic. Okay, so if you have forgotten, I'll leave the link for vernier caliper in my description below so that you can take a look at it and do a quick revision on how to use vernier caliper and also your micrometer screw gauge for both errors, for at least for the basic of reading the reading of vernier caliper and the reading of micrometer screw gauge. Now, question 3 is a tip to tail. We are given here is we have 2 forces, 3 and 4. Okay, they can be in any directions. Okay, but based on the question, there is a second constraint. Is that the first constraint is that we need to use these 2 forces to have a resultant force. The second one is that the forces orientation is 0 to 90 degree. Okay, so normally what I do is I will actually identify the forces that is available, that's possible at these 2 orientation. First, for example, at 0 degree and 90 degrees. At 0 degree, it will mean that if they are 0 degree apart, it means that the 3 Newton and the 4 Newton are actually pointing in the same direction. Okay, so at this particular instance, okay, the 2 forces at the same orientation, at the same axis, the maximum force I'm looking at is actually 7 Newton. Then the other one that we are looking at is that they are 90 degree apart. 90 degree apart here, we are looking at maybe it could be 4 Newton is here, 3 Newton is here. Okay, so we have a resultant force in this orientation. So if you do the simple tip to tail or parallelogram method, you will find that 4 Newton is here, tip to tail, 3 Newton. So the resultant force here will actually be easy of a 5 Newton, where the resultant force in this orientation is actually 5 Newton. Okay, then the resultant force at 0 degree, it will be 7 Newton. So between 0 to 90 degree, the possible forces that will appear actually ranges from 5 Newton to 7 Newton. So any forces between 5 Newton to 7 Newton between the angle of 0 to 90 degree, it is possible. Okay, so the only forces that won't appear between these 2 orientation, between 0 to 90 degrees, okay, the forces will actually be 4 Newton. So 4 Newton is out of the range, so definitely 4 Newton will not appear. Okay, so just take note. This question is actually quite interesting because most of the time they usually give 0 to 180 degrees. Now, question 4 is a classic example of scalar and vector. Okay, based on the questions, it takes 5 seconds to travel from P to Q, okay, 5 seconds to Q to R, and followed by 5 seconds from R to S. Okay, so this is I would say like what the question is given. Okay, so the distance is given there. So if I'm looking for average speed, the one that I'm concerned is actually I need the total distance. Okay, if I'm looking for velocity, average velocity, the one I'm concerned is actually I'm looking for the total displacement. Remember, displacement is a vector, is actually the shortest distance between the start and end point. I actually start here, I actually end here. Okay, so for displacement, okay, the displacement is the shortest distance between the start and end point. So the shortest distance between both of them is actually this straight line here. Okay, so actually for displacement, for a journey of P to S, I'm looking at actually at 10 meters only. For total distance, is the actual physical path that traveled. So I actually travel from P to Q is 10 meters, 10 meters, and 10 meters. So I actually travel a total of 30 meters. Okay, in 15 seconds. So both of them, the time taken here will be 15 seconds. This is common between them. Okay, 15 seconds. This is 15 seconds. Okay, so average velocity, it will be 10 divided by 15. Average speed here we will be looking at will be 30 divided by 15. Okay, unit will be meter per second, meter per second. And with this, you'll find that the answer, okay, will actually be straightforward, will be speed will be actually 2 meters per second, and your velocity will be 0.67. Okay, so the answer here will be B. Okay, so just take note of it. For question 5, okay, question 5, we are looking at the ball falling under free fall, under gravity, freely under gravity, and it start from rest. Okay, start from rest, okay, it's fall freely under gravity after release. That means the ball is actually at a certain height already. So this information will tell us that at the starting point times 0, it has to be a certain number here. It is a certain number. So which means this will tell me the height. Option D is out straight away. Okay, and since we know it's falling freely, so it means that the velocity will be increasing. Okay, and we will know that it will increase at a fixed rate. It will increase at a fixed. If it's ideal, it will be increasing at a fixed rate. Okay, if it's ideal. Okay, if it's ideal, why no air resistance? It will be increasing at a constant rate. Okay, why? Because that rate is actually known as the acceleration, which is 10 meters per second square. Okay, increasing at, okay, so this is what information is given to us. We will know that if the velocity is increasing at a constant rate, okay, it's increasing at a constant rate, which means the velocity will never be a constant number. So which means option A will be wrong, because for distance time graph, for this for height T, okay, you'll find that the gradient here refers to the rate of decrement of the ball itself. So this will actually give us an indication of the speed of the ball himself. So you'll find that the gradient here is actually constant, which will actually give us an indication that it actually represents the drop of the ball, the speed of the ball to be actually a constant number. Okay, but in this case, we know that the speed of the ball is actually increasing at a constant rate. The ball itself, the speed itself is actually increasing, getting faster and faster and faster. So based on that, the rate will be different. So that's why B is out. A is out, sorry, not B, A. Okay, then after that, what we're looking at is the height between B and C. B and C, the answer, for those who are sharp enough, you know that the answer will actually be B. Okay, one answer will actually be B, because when the ball is dropping, okay, the longer the time, okay, the ball will actually be traveling at a faster speed. So which means the ball will actually be dropping to the ground faster and faster and faster. So you look at the decrease in the time. Okay, so you look at the, I would say, like, you look at the decrease in the speed of the ball. You'll find that, okay, you'll find that the ball actually, the time taken for the ball to travel the distance, okay, especially towards the later part of the journey, while it's getting nearer to the ground, you'll find that actually, as I go nearer to the ground, the speed of the ball is actually much faster than the initial stage. So which means that the ball at the final stage should actually cover more distance as compared to the initial. Okay, and based on the graph of B and C, you'll find that the distance covered for graph C, for the later part of the journey, is actually getting bigger timing. Okay, based on the phenomenon is that as the ball drops, as it gets nearer to the ground, the time taken to cover distance should actually be shorter and shorter. Okay, because it's actually getting very fast. Okay, so actually what it should represent is that the speed time taken here to cover this amount of distance, okay, should actually be shorter. Okay, because the speed is actually getting faster and faster. That's why between these two graphs, although they are very similar, but it's just that the rate of decreasing of the height will actually give us an indication of the speed, how fast the speed is. And because of the indication, this graph, okay, this change, okay, this time will actually tell us that the option for the scenario described should actually be B. Okay, the B will actually describe the scenario given in the question. Okay, so just take note of this. Okay, for this question here, is actually quite tricky because it needs the students to actually analyze the drop of the ball with respect to the distance and speed, but looking at different segment. Okay, the initial part of the drop and maybe the final part of the drop with respect to the distance and the speed. Okay, which is actually quite a good question. Now for question 6, okay, question 6, we are looking at the ball being released from rest above a surface, ball released from above the surface. So which means at this point, this is the point of release that I mentioned. So which means while it going this way, while the speed is increasing, the ball is actually going nearer to the ground. Okay, so at this point in time, where upon the first impact dropping, this is actually hitting the ground. Okay, I'm hitting the ground already. Okay, I'm hitting the ground. So this is how you look at the graph. The more I hit the ground, and you find that the speed actually swing to the other side, the negative side. Okay, this will indicate that the ball actually, this is going down. The speed is actually downwards. Okay, on the other hand, this side here, you indicate that the ball is going up, so the speed is actually upwards. Okay, the direction is actually upwards. Okay, so just take note of your spelling. Okay, this is actually upwards. Okay, so this is what the jagged shape or this sawtooth shape is trying to tell you. Okay, the ball is actually hitting, is actually reversing in direction, is actually going up or going down. Okay, so based on this, you'll find the X. Okay, so what happened is the speed is going up. So now what happens is as the ball go up, and you find that at the moment in time, this actually stopped for a while. The speed actually stops, and you find that the speed actually becomes positive. Positive now, what happened is this. If upward is the negative means going upward, so positive will actually means the ball is actually going downwards. The velocity is going downwards. Okay, so what this means is that at point 0 here, at this 0 here, this point here, it indicates that the ball is actually at its highest point. Okay, this is actually indicating it's the highest point. So the ball will be dropping down, hit the floor. After that, swing down, you'll be going up, rebound, go up. At the highest point, you'll stop for a while. Then you start to come down, and after that, hit the floor again. After that, reverse direction, and the whole cycle will repeat. So essentially, what we are looking at is actually X and Y there. Okay, so area X and Y are the same. Why? Because obviously, okay, because X actually indicate the distance that's going up, and Y actually indicate the distance that's going down, and they are actually the same. Okay, so now in this area here, you will find that the answer here will actually be, if you analyze the graph, you will find that the answer, okay, between the answer, for area X and Y, if you know what they mean, they actually refer to the distance. Area under the graph of velocity time graph is actually distance. And this would mean that for X and Y, okay, because in looking at the motion of the dropping, you have to analyze from the graph, you'll find that X and Y is actually the rising and the falling distance. Okay, and because of that, the answer has to be the same. Okay, so that would be the distance between the impact. Okay, so you just take note of the answers, the wording. Okay, you have to analyze the graph carefully before you come to this conclusion. Now, question 7. Question 7 here, we are looking at car position A and B. Is that since both of them are looking at constant speed, you can actually use distance there by time because the speed is constant. Okay, distance there by time because it's for constant speed. So in this case, you'll find that A and B, okay, for them to catch up, for A to catch up with B, both of them must travel the same distance. So to catch up, distance traveled by A must actually be the same as distance traveled by B. That's for them to catch up. So distance will be velocity times time or speed times time. Okay, so this will be the A time taken. Okay, it will be A, B time taken. Okay, so both of them, you'll find that both situations, both will have the same time, same distance. Okay, catching up means actually they will catch up at that instant. So both of them will actually have the same time. And at the same time, you'll find that based on information, A is behind by B. A is behind B 50 meters, which means the distance traveled by B will actually be every time will be 50 meters more than A. Okay, because of this additional thing. Okay, so which means A must actually travel an additional 50 meters. Okay, and based on this information, you'll find that, okay, you sum in the value here, it will be A is 30 times T. This will be 20 times T. Let's put a bit of algebra here. Okay, then immediately you will know that 10T is 50. T will actually be a second. Okay, so immediately 5 seconds. So the answer here will be D. Okay, so one thing to take note is when you're looking at this type of catching game, okay, you need to know, okay, saying speed doesn't mean they catch up. For catching up, the important thing is about that they must actually travel the same distance. Okay, so this one I would say is quite straightforward. Now, question 8. So we have weighing machine. Okay, so the person is inside. Okay, now the mass of the boy is 40 kg. Okay, the mass of the boy is 40 kg. So if you look at the weight, so this will automatically be 400 Newton. Okay, so the boy will be 400 Newton downwards. Okay, and the leaf is moving upward. So the leaf is moving upward. So I would say just follow direction, take up as positive. Okay, at any one point, after there is a deceleration, based on the question, there's a deceleration of 2 meters per second square. Oh, see, deceleration. So there will be a negative 2 meters per second square. Okay, and actually there is a weighing machine. Okay, the weighing machine, based on information, it reads the normal contact force. So the contact force, where is it? The contact force is actually here. Okay, this is the normal contact force. Okay, so what is the reading in the weighing machine? AKA, this means what is the reading for the normal contact force? I want to find the normal contact force. So this will be same as before. Let me take a look. Okay, this will be, okay, so this will give us to Newton's law. Okay, so F net equal ma. Okay, since I take up as positive, it will be N minus the weights. I'll say give this symbol. So this is weight. Okay, N minus W equal to MA. Based on the question, answer is fine. And M is weight is mass times G, which I know. Mass of the boy is 40 kg, so it's 40 times 10, which is the gravitational field strength. Mass of the boy here is 40. Okay, now here take note, the acceleration based on the question, the acceleration here is actually -2, but it's a deceleration. Okay, so the acceleration will actually be a -2. So there is a -2 here, -2 meter per second squared. So this will be -80. This will be 400. Okay, so if you work out the math, it will be N will be 400 minus 80. It will be 320 Newton. Okay, so N will be 320. It will mean that the apparent weight is actually 320 and apparent mass in kg, 1 kg is 10 Newton. So if you convert 320 Newton, it will automatically become 32 kg here. Okay, just take note of the answer. So this answer here will be B. Okay, now let's take a look. So the first statement said the force on the ball, the force of the ball on the panel is the same as the force of the window panel on the ball. Okay, so which means if I have the ball here, I have the window panel. For me to break the glass, the ball, this the black color for ball. For me to break the glass, okay, the ball must exert a force onto the window. So the ball is on window. Similarly, the window will actually apply the equal and opposite force, opposite direction on the ball. By the window will apply a force onto the ball, opposite direction. So these two must actually, they must be equal because they are based on Newton law, they are opposite, equal and opposite forces. Okay, so immediately A, you know, is right already. Okay, because they has to be the same magnitude. It's just that they are in opposite direction. So straight away A, I will choose A as my answer already. Okay. Now, electric motor 500 kg vertically up. What's the power of the motor? Okay, so in this case, if I'm lifting up the concrete, you will find that the useful energy is what I need to lift up. So this, whatever energy I have actually is go to potential energy. So it will be mgh. Now, once you have the formula, let's sub in the item, let's sub in the variable. The mass of the object is 500 kg. Okay, the gravitational strength is 10 Newton per kg, and the height travel is actually 8 meter. So this is 8 meter. Okay, so if this number, you look at your calculator, you will give you 40,000 joules. Okay, and this will be actually the useful energy. So the useful power will be energy divided by time. It will be 40,000 joules divided by 4 seconds. It will give us 10 kilowatts. Okay, and based on the question is that there is a 50% efficiency. So which means if I put in 100%, if my motor put in 100%, 50% will be wasted, and the other 50% will be useful. And in this case, okay, the useful energy is 10 kilowatts, which is the 50%. So my power 100% will actually be double of my 10 kilo, which actually be 20 kilowatt. So the answer here will be 20 kilowatts for my motor. Okay, that's the power of my motor. Next will be B, okay, which is likely position of the center of gravity, just about to topple. Just about to topple, usually the moment you see this, you will find that the CG is actually at the pivot area. Okay, so if this is the pivot, just about to topple, in this line, the only option that is available on this line actually will be B. Okay, so I will know that the CG of the object is actually at B. Okay, because of this information about to topple, it will mean that the CG is actually at the pivot itself. Okay, so straight away option is B already. How about 11? Okay, 11, you have a bungee jumper. Okay, getting ready to jump. Now, for bungee jumping, especially with elastic cord, okay, student, you have to remember is that the way the elastic cord works is that if you are here, okay, let's say you are here, so there will be a few stages. So let's say you're in between, let's say you're somewhere at this point, I would say at initially you're A, then followed by B. Then after that, there's a position C here. Now, take note is that one thing to take note is for elastic cord is that elastic potential energy is only available if the cord is actually stretched or compressed, or the spring is stretched or compressed. So while B, let's say B, this is the full length, not stretch, full length. Okay, full length, or what we call the unstretched version. So if it's unstretched, the energy that you're looking here is only a mixture of, I would say, EK and EP, kinetic energy and potential energy. For stretching, right, for elastic to stretch, you need to, for spring, whereby to have elastic energy, you have to stretch and you have to compress. So upon full length, after full length here, any length beyond B, or to be exact, B to C, the spring or the bungee cord is actually being stretched. So the moment it is being stretched, you will find that elastic energy will take place. Energy will be converted to elastic energy because the cord is actually being stressed out. So there will be elastic potential energy at this point in time. Okay, so whatever energy I have at this point at stage B, okay, kinetic and potential energy, I will actually slowly convert to elastic potential energy until it is fully stretched. Okay, so while I'm stretching, okay, to be stretching while I'm stretching, energy will be converted to elastic energy, and similarly, there will still be EP and EK. Okay, but take note, the moment I reaches the lowest point, this C, I have a name for it. Usually it's called the fully stretched point. Okay, fully stretched. If you are fully stretched, it means at this point, the spring is at its maximum length, stretch length. And the item or the bungee jumping is actually not moving anymore. It's actually momentarily at rest. So this will actually be a full EE, elastic energy. This will be what we call the maximum elastic energy. And it will only take place when it's at fully stretched. So at fully stretched, the only energy we are looking at is elastic potential energy. So in between, okay, at full length, unstretched, we are looking at energy that doesn't include elastic energy. Okay, so for students dealing with elastic, you have to think, when does elastic energy take place? Okay, the keyword that we're looking at is stretch or compress. Okay, so just take note of it. And once you're clear about it, you will know that if I'm looking for the position whereby I have elastic potential and kinetic energy, okay, converted, okay, where elastic energy converted to kinetic energy, then you will find that the point, kinetic energy and potential energy, it will not be at the bottom, because at the bottom there will only be elastic energy. Then similarly, I will not be before I jump. Okay, because before I jump, there won't be any elastic at all. There won't be even be kinetic energy. On the way down, before I start to extend, before I start to extend means there isn't any elastic energy here. Okay, so that's why it will be, the best answer here will be on the way down as it decelerate. Decelerate here actually means that the cord is actually being stretched already. So to be exact, it's actually being stretching. So which means the spring is actually trying to slow the bungee jumper. Okay, so it means it's actually stretching. So this is actually in between B and C. Position will be in between B and C. So that's why my answer here will be C. Okay, so take note of the bungee jumping. It's quite interesting, this question. Barometer here, I would not say this is difficult. It's a classic O-level question. So if you have any questions, you can actually look up the O-level 10 series paper. It's actually quite a standard question. Okay, but if you have, so that's why I'll be going through. For those who have done, you'll find that C, for this number 13, the question is actually D. Okay, so if you have any doubt, okay, just let me know. Yeah, I'll go through it with you again. Okay. For question 14, okay, question 14 is barometer is a bit of mathematics. Okay, this is why we just look at math. Okay, now remember the idea of a manometer here is actually to look at to use the formula H rho G. And normally for manometer, I will always advise students to always look for the height, or look for the height whereby the liquids between the two limbs is actually the same type of liquid. Okay, because for them to have the same pressure, H rho G, one of the conditions, the criteria is that the two limbs must be of the same height, they must have the same density, which means they must be the same liquid, and they must be on the same planet. AKA the height, the limb that you're looking at, it should be here. Okay, because at this point, both limbs will actually have liquid Q inside. Okay, so which means at liquid Q, PQ will actually have the same pressure as maybe PR, point R. Okay, so in this case, it will be PR is actually the same as PQ. Okay, so the pressure will be H rho of Q, okay, plus the atmospheric pressure, which is here. Okay, as for R, R will depend on the liquid above it, which is here, okay, which is actually a layer of liquid Q, actually. So you will actually have, okay, so for Q, I will actually have P atmospheric, which is here, the atmospheric, plus a layer of liquid here, which is 2x, okay, H. Okay, let me take a HQ. Okay, in this case, this will be HR and rho of the liquid, which is P plus gravity. The left side PATM and the right side PATM, they are same number. They can actually cancel with each other. So after that, I will sub in the number. So HQ, okay, is actually here, which actually corresponds to the distance X. Okay, so actually I can replace it. Okay, so I will take HX, this to be X, rho Q is here. And similarly, my G I can cancel because they are same number. Then HR HR here, in this case, HR, we actually refer to here, HR, the whole length of HR here, this will be 2x rho P. So now once you have this, I want the ratio of P is to Q. So which means I will have rho P over rho Q, x over 2x. So the answer will be 1:2. This manometer, this mathematics, although it looks complex, but actually it's a standard way of whereby we apply the formula or HOG to manometer. Okay, so I would say it's a standard approach. Now for question 15, hydraulic pump. Hydraulic pump, the first thing that we look, the moment you see hydraulic pump, the first thing students have to be aware is that the pressure on the left-hand side P and the pressure at the left-hand side Q, despite what the sizes, you'll find that the two pressure is actually the same. Pressure, but not the force. Okay, the weight of Q divided by area of Q. Okay, if I'm looking at P, it will be the force of P divided by the area of piston of P. Okay, so it'll be force of P divided by area of P. So in this case, since for the ratio to be the same, for the pressure to be the same, if my force and area is small, for them to have the same ratio, okay, I can actually, if I can actually make that area of Q to be big, and I will actually have a bigger force appearing on the other side of the piston. And bigger force, bigger area, but the ratio is still the same as a small force, small area, or what we know, the ratio, or what we know as the pressure. Okay, so if I have so basically what you're looking for hydraulic is like, since the pressure are the same, the surface with the big area, will have a big force. Surface with a small area will have a small force. Okay, so in this case, if you look at the force and pressure, so this is what you need to know about hydraulic. Okay, first thing is you need to know they are the same pressure, and the other one is about this roughly the size and the piston area being linked together. Okay, so with this in mind, you will know, after reading, you'll know that actually the answer here, okay, this answer here will actually be correct. Okay, they have the same pressure. P will actually be, this is P, force will actually be smaller than the force at Q. This will be force at P, will be force at Q. So it has to be smaller because it has a smaller area. This is correct. Then after that, you'll find that the distance moved down, okay, by the pressure at Q. If B is correct, automatically C is wrong already. Okay, because pressure has to be the same. So automatically you know the answer is C already by understanding how piston work, the basic of hydraulic press. Now for question 16, is straightforward, double gazing. Okay, losers hit. Why? Okay, for losers hit. Why? Because air, double gaze, the idea of double gaze means there's an air inside and there's a two layer of glass. In between there's air. And the idea of us using air is because air is a poor conductor of heat. So straight away, I know this is the answer already. Okay, double gaze window, quite a common thing. Aluminum foil wrap around the foot. Okay, which side is shiny? Okay, remember shiny, shiny. Okay, I need to cook the foot. So now I need to cook the foot. So for the foot to come to cook fast, I will actually have to make sure that, okay, this is my foot. Okay, I have to make sure that my foot enter the aluminum foil as fast as possible. So which means that first thing first is I have to make sure as fast as possible means actually the downside has to be outside. Because the outside will be a good absorber. Okay, and the underside or the inside, okay, the inside here will actually be shiny. Why? Because shiny is a bad absorber. So if I absorb the heat in as fast as possible, I want to make sure the heat actually stay inside there. So if I want the heat to stay inside there, the interior surface, it has to be shiny so that I will not absorb as much heat, okay, as possible, keeping the heat for the foot himself. So it will have to be outside. So down will be outside. Okay, down should be on the outside. Down should be this will be out, but this stays shiny. So possible answer A, B, or C. Okay, same thing. If I have to be outside, like I mentioned, we're looking at down surface because it is an absorber. Okay, so automatically the answer here will be B. Okay, so answer here for 17, answer here will be B. Okay, better absorbers. Color refer to radiation. Okay, now for 18, okay, thermometer. For thermometer, necessary requirement. Some of us, we tend to confuse. How about the property for linearly? Now, linearly is actually not a necessary condition to choose thermometric property. When we say linearly, it's not a necessary. It's just convenient. I prefer linearly. Why? Because it makes it easier to calculate. Okay, because for every 1 degree, I will increase by 10 degree. For every 1 cm, I will increase by 10 degree. 1 cm, 10 degree, 2 cm, 20 degree. So linearly, it's easier for me to calculate. But it is not a necessary requirement. It's good to have, but it's not necessary. One of the necessary condition is it to be continuous. So which means that if my temperature increase, the particular property will have to be increasing. So for every increment, the property has to be increasing. So it has to be continuous. It can be decreasing also. So for every increase in my temperature, okay, the property can decrease. So as long as the trend is actually fixed, it's actually continuous. Okay, that thermometric property is one of the more essential than compared to linearly. Okay, when we say continuous, when we say continuous, it can be opposite direction. In every increase in increased temperature, the property decrease, or it can be same direction. Okay, increase and increase temperature, increase property. Okay, as long as it's continuous. Another way of saying continuous is that for every every temperature, there is only a particular value for that property. Okay, so as long as my length increase, you indicate the temperature increase. Okay, or my length decrease, indicate for every indication of temperature increase. So as long as the trend, okay, is continuous, is fixed, okay, that particular property, that thermometric property is actually what I need to make a thermometer. In other words, it's saying that for every value, for every length, okay, for every number, it actually corresponds to a particular temperature. So there isn't any like double counting. So for length 2 cm, it actually corresponds to a particular degree, not both, not 2 answers or 3 answers. Okay, so just take note of it. For the answer here is actually number A. Now after 18, let's look at question 19. Okay, question 19 is about lenses. Okay, so to do lenses, one of the important things that I always remind students is actually to know, firstly, the 3 ray diagrams that the students need to draw, and how to draw them. And second thing that they must know is that the 6 basic lenses scenario. Okay, whether the object is at more than 2f, or is it on 2f, or in between f and 2f, and maybe on f and less than f. Okay, so these are the 6 scenarios that the students they have to take note of. Okay, and not just how to draw, and also details like the image distance, object distance, image size, image characteristics, and even the users. If you are well versed in that, okay, I will find that question 19, you will not have actually much problem for this. Okay, but if you have, okay, I will leave the link to my lenses video in the top right hand corner, so that you might want to click on it so that you can do a quick revision for lenses. Now, if not, let's look at question 20. Question 20 is a refraction question. Now, it talks about identifying the object with which path is not possible. Okay, now for glass block or for refraction, the important thing is whereby we have to always tell students that it revolves around like the motion, the path of the light ray. So where from dense to less dense, okay, you should know that it actually bend away from normal. Okay, so if it's less dense to dense, okay, so the path should actually bend towards normal. Okay, so these are the 2 characteristics that we always make use of when we look at refraction. So to test whether the path is right or wrong, we look at whether the bending of the light is actually correct orientation. For example, let's look at question 1. Question 1, let's say if I look at the normal of the lens, okay, so the original path, the incident ray is on these surfaces on the left. Okay, so this is a less dense medium. The glass block is a dense medium. So the path should actually bend towards normal. Okay, so the original path for the incident ray is here. So they find that the final path in the glass block is actually bent towards the normal. Okay, so this particular path actually is correct. Okay, so from less dense to dense, the path actually bend towards normal. Okay, and like vice versa. Okay, when the ray is at the glass to air medium, the moment he hit the glass block, when he hit the glass block and he exit from the glass block, this is a less dense medium. So the light ray actually should bend away from the normal. So judging by the path, okay, I find that option A, the path is actually the correct one. Okay, so if for this particular path, for this particular question, I wouldn't say there's any shortcut, except like you have to do it one by one, test one by one. Okay, until you arrive at the correct answer. For example, D, I would say the normal is here. Okay, so this is the normal. Okay, so based on this, the angle of incidence is here. So this is less dense medium. The glass is a dense medium. So if it's dense medium, it should bend towards normal, which is what this path actually depicts, which is correct. But one of the things that students have to be careful is you take a look at the incident area on the normal at the right hand side. Okay, this is the normal. Okay, for this particular surface. Now at this surface here, okay, you'll find that the incident angle of this surface is actually this particular angle here. Okay, based on alternate angle. Okay, which means that the refracted angle here for these surfaces is actually the incident angle for the opposite side. Okay, so because they are the right angle, they are the same angle because they are alternate angle. So in other words, that if this is the incident angle, it should actually exit, okay, the glass block, okay, based on the principle of reversibility. Okay, so which means if my angle enter here if my light ray hits the surfaces at example 40 degree, the refracted angle here is maybe 20 degree. Okay, similarly, if I hit the surfaces at 20 degree, I should actually exit the surfaces at 40 degree. This is what I mean. This is what principle of reversibility means. Okay, mean the angles, it goes both sides. Okay, both goes the angle, it goes direction, both direction. So it should actually bend away and it should actually be at 40 degree. Okay, so which means at these surfaces here, the incident angle is actually 20 degree, or what we commonly say the incident angle at these surfaces is the same as the refracted angle. Okay, and thus the refracted angle should actually have the same angle as the incident angle on these surfaces. Okay, so which means the ray on the right side should actually exit the block. It should not actually do a total internal reflection. And because of that, option D is actually wrong. Okay, so just take note of this. For this particular question, I don't see a shortcut except like you have to try one by one. Now, for question 21. Okay, question 21, we're looking at it. You are given two refracting index. One is water and one is glass. Okay, glass is 1.5. Water is 1.33. Now, to calculate the critical angle of glass, okay, so the formula will be sine critical angle sine C equal 1 over n of the glass itself. Okay, so I want the refracting index of glass. So the formula will be 1 over 1.5. Remember glass, I'm looking at the refracting index of glass. So this is the one I need, 1.5. Okay, so you look at the map, this will be sine C. This is the critical angle I'm looking at. Okay, so angle C will actually be the inverse of sine, okay, 1 over 5. So if you look at a calculator, you'll find that the angle here we are looking at is actually 42 degree. Okay, 41.6 or 9, something like that. Okay, so you round off, it will be 42 degrees. So the answer here will be B. Here, just take note of it, because you are given two refracting index, water and glass. But because I use glass because the question asks for the critical angle of glass. D, which of the following is false about sound? Okay, sound radio wave. Okay, remember sound is actually anything related to sound is actually your longitudinal wave. Okay, radio wave is actually your transverse wave. Okay, transverse wave means it travel at 3 times 10 power 8. Longitudinal ultrasound is travel at much slower. Okay, and same thing, transverse wave by default it can travel through vacuum. Okay, radio wave is transverse. This is longitudinal. This is correct. Okay, radio wave is 3 times 10 power 8. Okay, and of course, ultrasound cannot travel through your vacuum. He needs a medium. So if R and that, okay, is actually, if A, B, C is correct, so you will leave down to D. Okay, that is wrong. Okay, so it's quite straightforward lah. Okay, for 23. Okay, 23 is I would say it's a classic question. Okay, because it needs the students to deduce the possible motion. Okay, the next motion of the wave itself. So one of the techniques that I always tell students is to take note of this direction of wave propagation. It tells you where the wave should move. So for example, in this case, okay, the wave this is the current position of the wave. So in that particular direction, maybe in a second later, at an instance later, the wave will actually move to the right because the question says the wave moves right. So actually the wave, it will look like this. At the instant later, the wave will look like this. So the red color one, it could be example, like it could be like maybe 1 second later. Okay. So the this is maybe t equal to 0 second. So 1 second later, the wave, it will shift to the right side. So which means that, okay, take note, okay, for wave particles, remember the wave is always vibrating at their own fixed position. So which means that originally the P is here. Now my P is actually upwards. So this is my P prime. Okay, this is my P prime. We actually move upwards. And vice versa, my Q, it actually move upwards also. Okay, to this position Q prime. Okay, so my P and my Q actually move upwards as the wave moves to the right. Okay, so at the instance whereby the Q is moving upwards, okay, which is the red color instances, okay, this is what the question is asking. What happened to P? In this case, based on what you deduce, P is actually moving upwards and it's above the equilibrium position. Okay, here, take note, students, you have to know where is the equilibrium position. This is the equilibrium position, the equilibrium or the zero position. Okay, so take note of it. Okay, above the equilibrium position, it will be upwards. So that's why answer is A. Okay, this way of shifting the graph, I would say, is quite a common. It's a neat trick, basically. Okay, so you still have to take note. These are some of the tools that you might want to equip yourself with inside your tool bag when you sit for exam. Now, loud. The question 24, loud and low pitch. Loud and low pitch. If you look at pitches and loudness, loud means both is loud means it is big, it's high amplitude. Okay, high amplitude. Low pitch, in this case, it means it is low pitch, it is low frequency, or sometimes we call this period. So the only graph that fits these two is with high amplitude. Okay, it will be these two, but it has a longer period. Okay, a longer period, it will be means this. Okay, the time taken for one cycle is so big. Okay, as compared to the small cycle here. So that's why the answer is A. A is the only one that fits large amplitude. And actually, what we call your long periods. Okay, the long periods. Okay, so take note of it. Long period or what we call low frequency. Okay, so this is what we depict by the, this is what depicts loud and low pitch sound. 25, just take note of it. 25, this question needs students to actually take measurements. Okay, because why the question also say it. Okay, based on the question, by taking measurement on the diagram, so you need to take actually your physical ruler and go and measure it on that day. Now, for wavelength, okay, wavelength based on the picture. Okay, first thing first, I will say I always identify where is the refraction and compression. Okay, so where's the refraction and compression is the point that it doesn't move. Okay, so these three are the points that's of question. Now, so which means if you analyze the neighboring particles, you will find that actually this neighboring particles here is actually getting further and further, which means R will be actually refraction. Okay, so if R is refraction, it means that the neighbor of it will be compression, which is true enough. Okay, you look at the particles is actually squishing towards the center of that particular particle Q. Okay, so P will be refraction also. Okay, in terms of wavelength, it will be from the point, okay, the equilibrium point, all the way to here. Okay, so this will be my lambda. Okay, this will be my lambda. Okay, so for this, you take a ruler. And likewise for amplitude, amplitude is the displacement, okay, of the particle itself. So you look for the maximum displacement. When you look for the maximum displacement, you'll find that, hey, this particular dot is actually the biggest displacement. Okay, so of this particular area. Okay, so what I do, I take a ruler, I'll measure the amplitude here. And with this, you'll find that the answer will end up with, so the answer will be C. Okay, C, 11.16 and 0.7. This is lambda, this is amplitude. Okay, so take note of the measurements. This is where you need to actually make a physical measurement itself. Okay, don't just expect it to be like you should be applying formulas and calculating. 26 electric field. Okay, if I suppose to put a negative charge, okay, why what happened? Okay, your unlike charge will attract, so which means my particle will actually be attracted to this positive charge, because why? Unlike charge attracts. Similarly, my particle will also be attracted to this particular charge here, because they are unlike charge. Okay, so basically because of these two charges, okay, the electrons will actually be pulled up diagonally to the left and diagonally to the right. And the combine of these forces will actually cause the particle to be exerted upwards. Okay, so this is the resultant force acting on the charge itself, moving upwards, okay, at the center. Because concurrently, he's actually being attracted by the positive charge on the left and on the right. So basically, it will be moving upwards. Okay, so just take note of this. Now, for the 27, you have your negative charge sphere. Now, take note, when you have a negative charge sphere, this is full of negative charges. Okay, if without the earth wire, okay, normally what happens is this. If without the earth wire, if I have a negative charge sphere, okay, let's say the thickness is sufficiently thick, you'll find that the interior, the electrons, okay, the electrons of these surfaces here will actually be pushed back to the back of the wall, to the exterior of the wall. Because why? Light charge attracts, light charge repel. Okay, so within the wall, the electrons in the cup itself, okay, the electrons will be pushed back because of repulsion, which means that by default, okay, the electrons is actually at the outside or the exterior surface of the container here. And when you have electron on the right side or on the exterior side, the proton will be only left at the interior side. So now what happens is, if the container is this way, and I happen to put a charging Irving cable, okay, same thing. If the electrons will actually be free to move, and the electron will actually flow out of the container, of the exterior container, and flow into the earth wire. And this is what we call neutralizations. Okay, the electrons on the outer surface will actually be neutralized. And what's remaining is actually the positive charges inside, okay, or the exterior. So the interior will be filled with your positive charges, because the exterior charges actually has been neutralized. And because of that, the answer here will be A. Now, question 28. The formula that we are looking at, okay, is what we know as R equal to rho L over A. And since area is pi R square, so and diameter is twice of the radius, so it will be R, okay, pi D square over 4. Okay, so, or in other words, resistance is actually proportional to L and D square. Okay, so this is the final relationship that we have, that relates your diameter with, relate your length to your diameter. Okay, so now what happens if I want the least resistance, okay, meaning my L, if I want the least, okay, for R to be least, okay, my L has to be smallest, my D has to be biggest. Based on the criteria, my length must be the smallest, so length automatically is 0.5, and my diameter has to be biggest. So between 1 and 2.5, B will actually fit the condition. That's why my answer here will be B. Okay, so take note here, we look at the formula R rho L over A squared, over A, okay, to see what are the properties that actually affects the resistance. Question C, total charge flowing 12 watts, okay, time of 50 seconds. What's the EMF? Okay, here the formulas, I would say I will not dwell too much on this question because it's quite straightforward of like substituting the formula. Possible formula you're using is P equal to IV. Okay, then after that you will have is actually current, potential difference is actually energy divided by charges. Okay, now 29, now 30. Okay, 30 we're looking at the finding the resistance. Okay, finding a resistance of the potential difference for a IV graph. Okay. Now for question 30 is an interesting one. Okay. Now the graph, he has an IV graph of a certain component. After that, he asks for the resistance of the component. We have voltage V1. Before we do it, let's run through the basic of resistance. Now, resistance in some of the questions or like maybe where it involve curves or even other straight lines, some of us tend to have this understanding, okay, that somehow R is actually related to the gradient, okay, of the IV graph. Okay, it's not wrong, but it's not actually correct also. Okay, so in this case, we are not looking at the change in I or change in B. okay, which will lead rise to maybe R is change in V over change in I. Some students even go to the extreme that we're saying that R is actually, well, delta I and delta V is like differentiation like that. Now, I will not say this is correct in the sense that if we go back to the fundamental of resistance, resistance is actually defined as the ratio of the voltage to the current flowing through it. So it's the ratio of V and I. Okay, the keyword here we're focusing on the word ratio. So in the sense that it's not about it's not about gradient. It's just that maybe sometimes the graph that is given to us, okay, the way we find, okay, it happened to be, like I say, IV graph. Maybe it's ohmic conductor. It somehow find that the V and the I, we use the V, we use the I. It somehow seems quite similar to like we actually finding a gradient. Okay, but in fact, it's actually not. It's actually the ratio of the I and V. What's the difference? Okay, what's the difference? It literally means that the ratio of the value of I and V. Okay, and the ratio is in the sense that the ratio is actually with respect to I would say the axis, to the zero. So here I'll run through the proper method of finding the ratio using an IV graph, and I hope it clear up the matters with you so that you don't actually judge did it wrongly. Okay, now if you look at other questions whereby maybe you look at if you look at like maybe a diode graph, get IV graph. Okay, sometimes like judging by the diode graph, you find that my graph looks this way. If I happen to use the gradient, it really explains the resistance, the change in resistance. Okay, but it's just by coincidence only. Okay, if not, it's actually using the correct method should be you analyze it through the ratio of the V and I. Okay, and you and after that you actually get the resistance of that particular at particular instance, and actually then you can conclude what happened to the conductor itself. But how do we look at the ratio of the V and I of the particular instances? Okay, here I will show you a technique that I said I always use and it always work one. Now, when we look at, let's say for example, okay, this particular for example, this particular point. Okay, if I want to look at the resistance of this particular point, I am actually not looking for the gradient. I'm not looking for the gradient of this particular VI graph. I'm not. The gradient of this particular VI graph doesn't tell me the resistance. In fact, actually what I should do is actually I should draw a straight line. Okay, I should draw a straight line to the axis, okay, to get the necessary V and I. Okay, so example, how do I find at this point T? Okay, at this point number 1. Okay, point 1. How do I find the resistance of point 1? So which means if I want to find the resistance of point 1, I should actually voltage of it at 1. Okay, and the current at 1. So how do I find the current at 1? Okay, the easiest one is actually connect it to the origin. Okay, so if I connect it to the origin, okay, so this I connect it to the origin. Okay, so this is the correct origin. Okay, so if I want to find the value of V and I at position 1, I am actually looking at this particular value. This is my V at 1. And after that, I'm looking at the current at the space here. I'm looking at, sorry, my mistake. So I'm looking at the I of at 1, and I'm looking at the V at 1. Okay, so which means these two lines will actually give me the I and V of this particular point, the resistance of this particular point. Okay, so similarly, what happens to the other point? Okay, so let's say I want to find the resistance of at point 2 here in this case. Okay, if you look at gradient, you'll find, this point 1 and point 2, they happen to be the same gradient. Then what happened? The resistance of this line will actually, the resistance between these 2 point 1 and point 2, it happens to be on the same straight line, so the gradient happens to be the same, and point 2 and point 1 will have the same resistance. But this analysis is wrong one, because gradient has nothing to do with gradient. Okay, it has everything to do with the ratio of the V and I. So how do I get the ratio of the voltage V and voltage I at 2? Okay, same thing, I use the same technique. I get a ruler, so I will draw a line cutting from origin, okay, to the point 2. Okay, so this is the point I'm looking at. So this is the line I'm drawing. So the ratio of this, the line, the vertical axis and horizontal, vertical line and horizontal line of this line, this purple line, will give me I current at 2 and the voltage at 2. So in other words, okay, so this will actually be my, this value here will be actually my current at 2. This value here will actually be my voltage at 2. Okay, so in other words, this is what I'm looking at. Okay, so this is my I2, this is my V2. Okay, sorry, this is my I2, this is my V2. Okay, so in other words, the gradient of actually is not the gradient of this physical line, this IV graph. It's actually the gradient of this line that give you the resistance of that particular point, at that particular instances. Okay, so in this case, you'll find that, okay, in this case, the ratio, the gradient of this line is actually the gradient of this line. If you take, okay, so it will be I2 and V2, which implies is a resistance 1 over R. Okay, so you'll find that as if you compare these two lines, okay, let's draw this line. Okay, so if you compare these two lines, okay, so let's say you compare point 1 and point 2. Okay, so let's look at this second line. Okay. Now, you'll find that by looking at the line, okay, you'll find that line gradient of line 1, the purple line. Okay, the gradient of line 1. Okay, let's erase this. Okay, the gradient of line 1. Okay, the gradient of line 1 is actually steeper than line 2, which means the gradient at line 1 is actually bigger than the gradient at line 2. Okay. Now, and based on this question, you know that the gradient in this case it refer to I1 V1. It refer to I2 V2. So in this case, it means that the resistance of 1 at point 1 is actually resistance is actually V over I. So in this case, okay, the steeper the gradient, okay, the inverse of this gradient will actually be resistance, because the resistance is V over I. So now I have I over V. So it's the reverse. So which means that the resistance of 1 is actually smaller than the resistance of 2. Okay, so you'll find that for this particular analysis, you'll find if you use this, you use the ratio, you'll find that resistance at point 1 and point 2, they are actually different number. Okay, unlike some of us who like to use this gradient to analyze the resistance, you'll find that R1 and R2 happen to be on the same straight line, happens to be a constant straight line, and the gradient actually is the same, which means the resistance will actually be the same. Okay, which is wrong, which is the wrong analysis. Okay, so with this, I hope actually students, you actually pay a bit more attention to the way you analyze the IB graph. And after that, all this, you'll find that actually the resistance of V1 based on the question is actually the answer D. Okay, so with this, I hope, okay, it makes sense, okay, or it makes some sense to the word ratio. Okay, ratio is not gradient. Okay, sometimes it looks very similar, but the deep down, the fundamental of ratio is actually not gradient. Okay, so take a look at this analysis. If you have any problems, you can just leave a comment at the video, or you can drop me an email so that we can actually discuss it out. Okay, if not, question 31. Now, question 31 is a circuit question. Now, what happened? They have 3 identical resistance. Okay, so this is in series. This is in parallel and series. Okay, now, so take a look at this. You will find that if they are identical, you will find that this is actually half of the resistance X. Okay, if you can't see it, okay, you just have to substitute some value inside, so you give a sense of the numbers. So let's say I will say this is 10 ohms. Okay, so this is 10 ohms, 10 ohms, 10 ohms. Now remember, the trick here is to understand what is parallel circuit. Now, parallel circuit, remember, the more resistance you jump them in parallel, the smaller is the resistance. So which means that the final circuit that you're looking at, okay, you'll find that this particular circuit here will actually be combined into a single resistor of 5 ohms. Okay, so you will find that eventually this circuit here will actually become 5 ohm circuit, okay, in series with the 10 ohm resistor, okay, connected to the cell. So this is the green color one. After the two parallel branch, the resistance actually will drop. In this case, you'll find that actually it has a certain value in the sense that it dropped by half because they're identical. Okay, so which means that 10 ohm and 5 ohms. If I say this is 1 unit, you'll find that the potential difference at the 2 ohm here will actually be 2 units. Okay, because 10 ohm is actually double of 5 ohm. So which means the potential difference will actually be double. Okay, so which means that if 3 units in total, 3 units, okay, control the EMF based on potential divider. Now, 1 unit will actually control 1/3 or 1/3 of the EMF, okay, which is what 5 ohm is actually controlling, 1/3 of the total EMF. And with this will tell us that the answer for the potential difference across Y is actually 1/3. Okay, so just take note of how we can use potential dividers and how we can use the series and parallel properties, okay, to our advantage. Okay, now question 32. Okay, question 32. What happened to the circuit? Okay, when switch S is closed. Okay, now switch S is closed. One of the important thing here is that we actually have a small short circuit here. When switch S is closed, this path is actually a short circuit path, which means that your current will actually travel through the red color path. It will actually ignore the 2 ohm path because the red color path is actually a perfect wire. So which means your resistance, your circuit here, when I close switch S, my resistance actually drops. And what happens is when my total resistance drops, So what happens when my total resistance drop? The current flowing through the battery will actually be increasing. So which means the ammeter reading will be increasing. Okay, and similarly now there's only one resistor. Previously there was 2 resistor. So there was this resistor and this path. So these 2 resistors will share 4 volts. So each of them will be 2 volts and 2 volts. But now with the path, with the switch S closed, this 2 ohm is short circuited. So I will have these 2 ohms entirely, okay, supporting the 4 volts. Okay, or these 4 volts actually supporting all the 4 volts actually supporting the 2 volts, 2 ohms. So as a result, the potential difference of these 2 ohm will actually increase. So you'll find that this is what happened to the circuit here. So this will be the answer that I'm looking for. Okay, so this is what I mean by you analyze the circuit based on the path, okay, based on the situation to identify what are the possible increment or decrement for voltmeter and ammeter. Question 33. Question 33, you have your LDR. Remember LDR, the idea of LDR is that the intensity, LDR, remember the one property that you have for LDR is the intensity actually will increase and resistance will decrease. Okay, remember intensity increase, resistance will decrease. Yeah. Okay, so now what actually happened? I want the light bulb to be brighter. Okay, I want the light bulb to be brighter. So what do I mean by brighter? So based on potential divider, if I want the light bulb here to be brighter, if I want B bulb to increase, to be brighter means the voltage must increase. If you reverse the thinking, you'll find that if my V bulb must be high to be bright, you'll find that the resistance across B has to be increased. So now with the light bulb V increase, the resistance across B must to be increasing. You'll find that the jockey here or the point here must actually go up to X, okay, to have a higher value, to have a higher resistance. Okay, so which means my P has to increase to X. Now, similarly, for me to command a bigger voltage, okay, for me to command a bigger voltage at VB, okay, for me to command the bigger voltage at VB, I must make sure that the voltage across LDR, VLDR, must be small, okay, or must be decreasing. Because these 2 components, the voltage of my LDR and the voltage of light bulb, they are actually supported by who? By the EMF. And the EMF is the constant number, is a constant value. So which means the bigger my VB is, the smaller my voltage of LDR is. Okay, so which means for my voltage LDR to be decreasing. So for my VLDR to decrease, okay, so that my voltage of light bulb can increase, you'll find that the resistance for LDR must decrease. Okay, smaller resistance will command smaller voltage. And for resistor LDR to be lower, the condition for this transducer to work is the intensity must be increasing. So which intensity increase means actually it means it is a brighter environment. Okay, so the next condition I need to have is actually a brighter environment. So which means I will actually have light incident onto the LDR. And the correct answer will have to be with the two highlighted one, which is A. A will have actually the possible options or two possible conditions that will achieve light bulb. Will have the two possible conditions that is necessary for the light bulb to become brighter. And as such, answer will be A itself. Now for question 34, okay, question 34, okay, a fuse, okay. So now what happened is you have a fuse in question and you actually have a worn out cable and you have actually a short exposed cable touching the earth wire. So now because of this fault, you will know that the current or the casing will be live. Okay, will be live, or aka current flow through the casing. Current flow through a casing, which means the first option that we're looking at, the casing is live and dangerous. Yes, definitely. This option is definitely correct. But then you have to look at what are the clues that's given to you. In this question, the question did tell you there is a fuse in the electric fan. Now, what happens when you have a large current flowing through? When you have a large current flowing through the fan through the fan itself, especially through the large casing. Metal casing, good conductor, the resistance will be low. So that's why the current will be flowing through the casing will be very high. So in this case, at the instance, my casing will be live. And what happens is that when my large current flowing through higher than normal, or what to be exact is higher than my fuse rating. So with that, okay, with current higher than my fuse rating, you will find that my fuse will actually be activated. The fuse will start to melt. And upon melting, you will find that, okay, when the fuse melts, the eventual outcome or the eventual state of this particular fan or with this particular fault is that the fuse will melt and the current will stop flowing. The fuse will actually will disconnect the fan from high voltage, and the current and the no current will actually flow through, even through the casing. And as a result, okay, A is actually a better answer compared to C. C, what I would say is that the answer, this only is like more like the initial stage or maybe the intermediate stage. The final stage is actually A, whereby the fuse will actually take place and will actually cut off the circuit. And that's one of the main reasons that we use fuse in our circuits. Okay. So just take note of this. Okay, in this case, it's quite a tricky question. If you find that the moment I have live casing, I will choose C and I will just skip. Okay, so here take note, students. Okay, read the question carefully before judging the answer. Okay, now question 35. Okay, if I have a north pole approaching the compass, okay, remember I had the keyword here is iron cylinder. Okay, so which means my magnet, the fuel line that entering the iron cylinder, it actually will not end up at the compass. You will not end up at the compass this way. You will not, because now your iron cylinder is a magnetic material and it will actually provide a shielding effect. So which means your magnetic field line will actually be moving across these particular surfaces, moving across the iron cylinder, and as a result, none of the fuel line will actually enter the compass itself. And as a result, okay, my compass will actually just remain at its original location. Okay, nothing will change. So that's now the question 3. Okay, question 36. Okay, is our Maxwell right-hand rule. Is looking at combination of like forces. If I'm looking at option C, so let's say I'm looking at X now. X is out of the paper. So if you look at a Maxwell right-hand grip rule, you'll find that X is actually gripping clockwise. Okay, out of the paper, clockwise. Okay, so which means the magnetic field line at X will actually be this way. Okay, so which means the magnetic field line will actually be like pointing to the right side. Okay, so this will be the field line for X. Then after that, you have your magnetic field line of Y. Magnetic field line of Y current is going through into Y into A. Sorry, going through Y is into the page. So if you use a Maxwell right-hand grip rule, you will find that the forces, the current going through Y is the magnetic field line going through Y. It looks like this. Okay, so between the current direction, the field direction will be maybe bottom right in this direction. Okay, so X will actually be this direction, the field line. Y, okay, the field line will be this way. Z, okay, if you look at it, Z into the paper, okay, you'll find that Z, okay, the field line will be this way also. Okay, so the field line will be more in this direction. So for Z, the magnetic field line will be in this top right hand corner. So if you look at O, in this case, O, you'll find that X direction will be to the right. That's the magnetic field direction for X. Y, magnetic field line at Y of Y, magnetic field line at O, okay, due to Y will be this direction. Magnetic field line, okay, of Z at O is this direction. And you'll find that this tree actually is pointing towards the same axis, which is pointing towards the right side of the paper. So if you add up all these three forces together, you'll find that these three forces, okay, you add up all these three magnetic field, the vectors, you'll find that eventually at O, the resultant field line will be towards the right side. This will be the resultant magnetic field lines. Okay, these will be the magnetic fields. Okay, so that's why my answer here is C. For this particular case here, right, I did not manage to get any shortcuts. I still treat it one by one. I still go through option A, B, and C, until I figure out the answer. In the sense that I will not say there's a shortcut to it, but nonetheless, if you manage to have, if you have one neat trick or shortcut, okay, kindly share. If you don't mind, you can share. Please share with me so that I can actually share with my kids, so that they know how to get this answer done more elegantly. Okay, so for question 37. Okay, 37 is an interesting question. Okay, 37, one thing we know is that we always will know that it's a light current, same direction. So you will have an attraction effect on both wire. Now, attraction is both way one. Attraction in the sense that the attraction is current A, wire A will actually attract wire B. Based on this attraction is like, I would say it's a equal and opposite action. Where A will attract B, B will attract A. And both of them, regardless of the sizes of the current, as long as, okay, if they are light current, you have this attraction force, you will find that the force of attraction on A is actually equal to the force on B. Because this attraction force, mutual attraction force, it arises from your Newton's third law, action and reaction. Okay, if A is attract B, B will attract A with equal and opposite forces. So these two forces, regardless of the size of the current, okay, the forces that will actually balance out to be the same. For question 38, okay, 38, I would say quite simple. Okay, I just want to make sure it's opposite direction. For your DC motor, okay, you just need to reverse one of the possible input. For example, I can reverse the North Pole and South Pole, or I can actually reverse the current. Okay, or I can reverse the battery. Anyone I reverse, I actually have the opposite effects already. So this one, straight away, you will know that actually the option here that I'm looking at is actually B. Okay. Option 39, okay, CRO. Okay. Now, take note of this. Okay, what is the maximum value of potential difference? For CRO, remember, if looking at a graph, you must know this is the neutral position. No voltage is applied, so this is the neutral position. So I'm looking at the maximum voltage. Maximum voltage, remember, this maximum voltage is actually measured from equilibrium to crest or equilibrium to trough. The maximum voltage here we are looking at is either measured from the equilibrium, it's always measured from equilibrium up to the crest or up to the trough, either one of them, which will actually be this red color line, which actually tells us this one you have actually 7.5 squares. Okay. So now take a look. In this case, the question says based on the bench, okay, based on the gain, the Y gain, it is 1 cm for 5 volts, or aka 1 cm is actually 5 squares. Okay, so 5 square actually will control 5 volts. Okay, so if I have 7.5 squares, 5 square control 5 volts, you will find that my answer here will be a simple 0.5 square. What am I saying? Okay, it's a 7.5 square. It will actually control 7.5 volts. Okay. So just take a look at the answer here. Okay. So it's a basic ratio. I would say it's a ratio question now. But for students, take note for CRO, remember the marking. Okay, remember the unit. Okay, for example, in this case here, we're looking at 5 cm, 5 volt per cm. So you need to take note for what 5 cm, what is the how many squares am I looking at? Because sometimes it's quite confusing. Now for question 40, it's the last one. Okay, this is a classic example of Lenz law or Faraday law and Lenz law. Okay, now when your spring is jumping up and down, same as bungee jumping or same as any spring oscillation, you need to know when is the maximum speed, where is the minimum speed. Okay, for example, for spring, okay, when it up here at P, this is where it is maximum compression. Maximum compress, the spring is maximum compress. At R, this is maximum stretch. So the spring is maximum stretch, it's stretched at maximum already. So then after that, what happens is you have the normal Q, which is the equilibrium position. Now, for bungee jumping or this type of spring question, you have to take note of certain key factor. For example, when you're looking at maximum stretch and maximum compress, as say for bungee jumping, the person jumping down from the cliff, he reaches the maximum end whereby the cord is actually being stretched. So the moment you have stretch and compress, there are certain characteristics. When you have maximum stretch and maximum compress, you'll find that the object or the spring itself will actually achieve what we call a momentary at rest. So you'll be at rest for a short instance. Why? Because these are the point whereby the spring or the object is actually getting ready to change direction. So that momentary at rest is just for a short instance whereby it stops for a while. After that, he will reverse the direction. So for example, at P, at P is the maximum stretch, means it's the highest already at the topmost position. So at that point in time when it reaches P, the magnet will actually stop for a while. Then after that, it will come down again. Okay, it will start to increase the speed. Likewise, if it's maximum stretch at R, maximum stretch at R, you find that the object is maximum stretch, means at the bottom already, it's at the lowest end already. So before since it's at the lowest end, the next instant is he must go up. So before I go up, I will actually have what we call momentary at rest to stop for a while before I reverse my direction. And for magnetic and for Lenz law, it's important because at V equals 0, the rate of change is actually 0. Okay, there's no movement, so there's no rate of change. So the rate of change is actually 0. And this no rate of change, it will imply the EMF induced is actually 0 at this particular position. So similarly, if you have similarly for R, the same thing will happen again. So the same thing for R is that you'll find that for R, there's no rate of change. Okay, there's no rate of change, there will no EMF, because at that instant R is maximum stretch, is at the lowest point, is about to return. So at that point, it will be momentary at rest and no rate of change, then the EMF will actually be the lowest, aka 0. But at equilibrium, when the spring is like moving down, it's increasing the speed. Okay, at equilibrium, okay, this is what we call the unstretched length. Okay, unstretched length. So it's neither stretched. Okay, not the spring is not stretched, or what you call the unstretched length, okay, of the spring. Okay, the unstretched length of the spring. Okay, at the equilibrium, or what you call the unstretched length, okay, you will find that this particular point, the spring will actually be the speed will actually be the fastest. The speed will actually be the fastest. Okay, you will run through position Q at the fastest rate. And because it's running through at the fastest rate, imply that the rate of change is max. Okay, the rate of change is max. And when you have rate of change max, okay, you will have one particular instances. You will only have one particular outcome. It will mean that the EMF induced is maximum. Okay, so you'll find that for this particular case, where we will find that P and R, although they are the tallest and the lowest position, you'll find that the EMF is actually 0. So which means for EMF induced 0, it will be actually position P and actually position R, because they are momentarily at rest at this particular location. And likewise, okay, you'll find that this will be EMF 0 and Q will be EMF maximum. And this will actually answer the question This is what the question wants, to identify what are the points with no EMF induced. Answer will be P and R. Okay, option D. Okay, now with this, we have finished the last question for this particular paper. Same as before, okay, I'll be going through other papers. Okay, just remember to like and subscribe. Okay, and remember to press the bell button so that you actually receive the notification. Okay, the moment I upload the paper, and if the paper is of interest to you, you actually may want to look and to see what are the mistakes that you make, what are the common mistakes, so they can actually clarify with your teachers ASAP. If you have any questions, or I have explained certain things not clear or wrong, okay, remember to give me a comment at the description bar below, and let me know where are the mistakes or what are the changes that you may want to see. Okay, if not, other than that, okay, this is where I end off. Okay, see you for the next video. Thank you.